right, hello. So our senior project is MEMS Diagnostic. I'm Elisha. My other partners are Karan and Mark. So the goal of MEMS Diagnostic, the main goals we wanted to touch on we wanted to avoid medical expenses, so other expenses like co-pays when you go see the doctor, you have to pay for a copay, as well as for the treatment. So that just adds a lot of medical expenses. We wanted to eliminate this by creating an at-home medical service. So we wanted to create a MEMS diagnostic device that you can use at home. This would be a lower cost to users, eliminating that copay, cutting down time and all of that, and as well as being able to distinguish between bacteria and viruses. You can see this little chart right here, the first figure. It'll tell you the differences between bacteria and viruses, which ones you can use antibiotics and which ones you can't. On to the background. In the background, we hit three major things. We wanted to focus on medical problems, limitations, and what our impact of this, but we wanted this device to do for this project. So the medical problem, we wanted to distinguish between bacterial and viruses, like I said before. Current limitations are there's no such device that uses the specifications that we use in our device on the market right now that you can use at home. So that's a good and a bad thing for us, as well as the limit of the impact of this project. We want to eliminate like I said, the time and money spent in a doctor's office by creating an at-home device that will test bacteria and viral infections and will let the user determine if they need to seek further help.
Alright, so this is our current prototype. As you can see, it's changed quite drastically from the previous semester. In figure 2, you can see a combined view and dimensions of the final design. Now, this is a design that's consisted of the outer shell and the internal structures. So you can actually see the internal structures on the right, which is figure 3. And the yellow parts are the parts where it leads from the channel to the reservoir tank. The light blue part is the top part of the reservoir tank. The orange peach color is the actual impedance channel. The cream yellow part on the top left is where the attachment from the nanofilter to the channel is. It's a 90-degree turn. And the white part is where your syringe would be placed horizontally, because we found out that it was the easiest way to ergonomically attach the syringe. Some benefits of the current device is it's a compact design, it's ergonomic as well, it's user friendly because it's much easier to install than the previous version. It's spill resistance because of the outer casing plus the snap-on clips we have every single place. It has a much larger reservoir tank where you can hold up to 10 times the capacity of the syringe. It's more sturdy and stable because previous designs, every time we put the electrodes on, it kept tipping over to the left, right. It was not stable at all. It's definitely much more 3D printer friendly. By this I mean there's no need of supports, nor is there any defects on a normal printer. It's much larger in overall size, and we found out it's much easier to use as well because of the larger body it has. And we can take a look at the video once more. So as you can see, we first attached the channel to the top of the reservoir tank, then we attached the lid of the channel. Now we're attaching the 90-degree turn from the nanofilter to the channel, the reservoir tank, the syringe holder, and now the whole device into the casing.
So we did two major tests. One was the nanobead impedance testing, which was designed to test if the filter was adequate enough to filter out nanobeads of different sizes from each other. And from our impedance testing, we found statistically different results between the mixed and the filtered beads. So we can conclude that it was working. And the other test was bacteria and protein impedance testing, and that was to determine if the impedance tester was accurate enough to determine if the protein was different enough from the saliva so that we could get an accurate reading. So we mixed bacteria and protein, and we found that the filtered was different from the saliva. We created an at-home diagnostic device that can detect a virus from human saliva. And we tested this with the real bacteria and viral analog. In the future, we plan on doing other tests with other bacteria and viruses. We hope to not get statistically significant data on the bacteria and virus. And later on, we'll move to human testing and create our own device's own crude impedance tester.